Lou.
Thank you, Matt. I really do appreciate you guys at Gilson. Always are first rate and taking the time to get this thing organized. And thank you, everyone who's on. I really appreciate you taking time out of your day and listening to what we want to talk about, and that's pressure measurement, as I call it, pressure measurement 102. Let's see what we're going to discuss today. First, we're going to define and show you what and how square law elements work. What are square law elements? Well, square law elements are orifice plates, Venturi tubes, pitot tubes, and averaging pitot tubes. These are devices that measure flow. Usually, they must be coupled with a differential pressure transmitter. So in that regard, these are near and dear to my heart in terms of flow. I am a specialist in pressure and temperature, have been for 4 years, and I'd like to think of. After we get done discussing these flow elements, then I'd like to talk about remote seals. Remote seals are a necessary thing in pressure measurement. In my opinion, I think we tend to use them a little too much in industry, but that's for you guys to decide. We're going to look at where error sources come for remote seals. Why do you have errors? What causes those errors? And then we're going to close with a few do's and don'ts about those remote seals. So, as Matt mentioned, anybody who has a question, please give a holler, use that chat function. I prefer to stop, answer the question right then and there, so we don't have to back through a bunch of slides and just take up time doing that. If you have a question, don't be afraid to ask it, please. This is not very, very formal. This is kind of informal, one engineer to another, for the most part. So, without further ado, let's see how some popular square law devices work. Well, this class of flow elements uses a number of different principles. First and foremost, remember that flow is a velocity times an area. You know how many gallons per minute, that sort of thing, and that comes from the velocity, but the gallons dictates the volume. So we do have that equation, rather simple, but nonetheless something that's critically important as to how these flow elements work, these differential pressure flow elements work. Another principle that is required to understand is energy. You have kinetic energy, 1/2 mv squared. I think anybody, my grandkids in high school learned that in physics right at the very beginning. And there's potential energy, which we usually think of as mgh, but nonetheless is related to pressure. So energy has these two forms, kinetic or motion, and potential, which is pressure, static. Last but not least is the Bernoulli equation. The Bernoulli equation deals with the pressure at any point along a line plus the kind of kinetic energy term plus the height term. This is height now, not pressure. This is the height along that line. That is constant. So if something changes height, then something else in this equation will change, either the pressure or the velocity, if I have a substantial change in height. I kind of think of that as if I do work going up a hill, I'm going to lose something. I've slowed down. Patricia, please reply with you. Oh, okay. That's some other thing, not for me. As I go up this hill, I probably lose some velocity, and I probably, at that point, gain some height and have the potential to do more work or potential energy. The Bernoulli equation is really related to the energy equation of motion plus potential energy being equal on either side of some change in either potential energy or kinetic energy. All right, the terms of Bernoulli were our pressure, the density of the fluid, the velocity of that fluid, and the height, as I said before. All right, continuing the discussion of square law elements, let's look in detail at an orifice plate. This is a flat plate, usually clamped between a pair of flanges. And the key thing with an orifice plate is this sharp edge. The sharp edge constricts the flow rate through this hole, and I have a larger diameter, typically the pipe ID, and I have a smaller diameter, which is this beveled hole that I put in that orifice plate. The beveled hole is critical. This sharp edge is how all of the equations and the assumptions on cutting an orifice plate, those equations assume a very sharp edge right here. All right, this is commonly called the beta ratio, the ratio of little d, the hole in the orifice, divided by big D, the diameter of the pipe. And the smaller I make the beta ratio, the more pressure will be generated by the orifice plate. Okay, now let's look at a different type of square law device, a venturi. A venturi is a section of pipe. It has some length to it. It has a certain number of diameters here at small d and a certain inlet, big D, which corresponds generally to the pipe size. Once we come through little d, the throat as it's called, the venturi has a section of pipe that's kind of a conical shape, and it then brings the flow back to big D. Once again, little d divided by big D is the term called beta ratio. The smaller little d is compared to big D, the more pressure will be generated by this device.
So, Lou, how do you know it's time to change the orifice plate as the sharp edge is no longer sharp?
Depends upon your process, depends upon if there's any particulate, maybe there's very little particulate. Once in a while, some crud comes down the line. One of the weaknesses that you're going to see a little bit later is that an orifice plate really won't work very well with a fluid that has any entrained solids in it. A venturi will, and we'll look at some of the reasons why that works or why that is so in a later slide. But the knife edge of that orifice plate is probably worn 2 days after you install it. How fast and how much you accelerate that velocity causes wear. Um, I'm, you know, orifice plates are not something, in my opinion, that you would use for custody transfer. You can't count on them. As I said, as soon as that knife edge wears, let me get the next slide up, and as soon as this knife edge wears, you start to diverge from the um, equations that you assumed when someone did the calculation that said 100 gallons a minute equals 52.4 inches of water for this particular situation. Um, there's no, if you're an orifice manufacturer, you say, oh no, it's going to last for months and months and months, maybe years. If you're a Venturi manufacturer, you kind of poke a hole at that theory and say, nah, my device is better. And it is. There are reasons why, and you're going to see that in a little bit, as to why Venturis kind of last longer than orifice plates, certainly. But um, it just depends. Orifice plates have their place. Most of us in industry, or most applications in industry, rely upon the same thing causing the same signal. An orifice plate, once this knife edge wears a little bit and gets a little bit rounder than it was when it was brand new, it's going to repeat. You know, when you have 50 gallons a minute, it's going to generate a certain flow rate. But in industry, generally, we don't care that it's 50 gallons a minute precisely in terms of precision. We're not doing custody transfer. We're trying to control a process typically. So the orifice plate from day to day does change ever so slightly. But what we know in industry is when that reading is 50 gallons per minute, my product is, I'm making product the way I want to. When it's 55, things are getting a little hairy. I'm pushing the line too fast. When it's 45, I'm going too slow. I'm not getting enough product. So we generally look for um, repeatability. An orifice plate on a day-to-day basis will give you fairly repeatable device readings. Maybe it's different than it was 6 months ago, but today is today, and tomorrow isn't so far away. And if it was 50 today and I was making good product, then tomorrow I'm going to look at 50 and make good product. Maybe in 6 months, 50 isn't so good anymore for product, but I've adjusted in my mind to say 52 is now the number I need to make good product. There is no hard and fast rule as to when the orifice plate loses this sharp beveled edge. There is no way to know it. Um, some of the process fluids, I would tend to think a thick process fluid would wear a bevel a hell of a lot quicker than, say, the gas would. And water somewhere in between those two. So there is no hard and fast rule. Okay. All right. Let's continue. Let's see how flow is affected by the orifice plate. Here I have lines that represent the velocity path through an orifice plate. Out here, where I have, many, maybe I have 10 diameters of pipe, the velocity vectors are kind of parallel to the sidewall of the pipe. That's fine. I can look at the velocity through the orifice and know that if I have a certain velocity out here at big D, the internal diameter of the pipe, when I come through the restriction that is the orifice or the hole in the orifice, I change the situation. Think of a garden hose. I take the water comes out of the nozzle, and depending upon the force with which it comes or the flow rate that I have that plume of water coming out here in a relative straight line and with a fairly well-defined diameter. And that's key to the way an orifice plate works. Let's see that. I have the conservation of energy happening here. I have kinetic energy, the velocity, and I have potential energy, which is the MGH term that we're used to. And on both sides of the orifice, the kinetic and potential energy must equal each other. If I look at that, I have flow defined as the velocity in big D, the diameter of the pipe. I have the area of the pipe that is defined and related to big D. So the flow in the pipe has to equal the flow times the area. I have a smaller area here in little d, so the flow must be maintained. So the kinetic energy term of 1/2 mv squared over here plus the potential energy as the pressure in the big diameter of the pipe, that has to equal the velocity times the mass here on the downstream side of the orifice plus its potential energy. Those are the terms that define I have a large area and a lower velocity here. Since I've restricted the flow, the velocity after the orifice is higher than the velocity upstream of the orifice. And naturally, the potential energy, since the kinetic energy is higher here, the potential energy is less, as I've indicated by the height of the water in this phony manometer, just to illustrate the point. So I have a difference in pressure now that's generated upstream from downstream with respect to downstream of this orifice. And that's how we learn or know that all I did was take the equation little d times velocity at little d and area times little d. All I did was bring that over to this side of the equation. So I know that the velocity here is higher than the velocity there. All right, that's the flow equation. Now, let's look at the conservation of energy. From the energy equation, I know that the difference in pressure between high pressure here upstream, because I have lower velocity, the pressure here is higher. I have higher velocity, therefore the potential energy term is lower. So the difference between those pressures is a constant times little d squared minus big D squared. And if I substitute back for little d, take this equation that relates to the ratio of the areas here in the pipe versus the area here where I'm measuring the pressure, then I substitute that back into this equation and I come up with the difference in pressure is the ratio of the areas times the velocity here minus velocity here. And I have that this is the area ratio of the areas minus 1. I won't do the math for you, is times VD squared. All I did was bring this into here, and I get this term minus 1 because I've divided that and that by V sub big D. Then the velocity here is the square root of the difference in pressures, hence the square law device, times a constant. And that's how an orifice plate works. So that's how we get flow out of an orifice. That's the principle, and that is why, as I said, they're called square root or square law devices. Is that fairly clear to people? It's merely a manipulation. I tend to think of it as I'm turning potential energy and kinetic energy on one side, the potential energy and kinetic energy on the other. And fine, all the equations come about from compressibility, densities. The density term in that 1/2 mv squared is why a liquid will generally give you higher differential pressures because the mass is higher compared to a gas, steam. So I'm not trying to drown people in math. Anybody who wants to get into that, that's up to the interested reader, as the textbooks that we all used to see say. All right, let's see how Venturi works. Here I have a Venturi. As we said, it's a section of pipe, another section of pipe that comes down in some shape. Okay, how this comes down from big D to little d is unique to each Venturi manufacturer. And how long a throat there is and the angle at which it goes back up to the original diameter, those are all variables with each different Venturi manufacturer. Okay, but principle is exactly the same. The velocity in the throat is much higher, as I show by the length of that line, compared to the length of the velocity vector over here at the inlet, V inlet. Again, it's the same principle as we saw in the orifice plate. The difference in those is, once again, conservation of kinetic and potential energy. And, that determines how the Venturi works. I know the area because this is a physical piece or section of pipe. So I know this area precisely, and I know this area precisely in the Venturi. And I know, once again, the 1/2 mv squared at the inlet plus the pressure at the inlet is the upstream energy, and the downstream energy is the velocity in the throat times the mass, and once again, the pressure in the throat. The difference with the Venturi is that I'm measuring this pressure in a section of pipe, not assuming a certain flow coming out of that orifice. And we're going to deal with that in a moment. And that's one of the limitations of the orifice plate and why it has some limitations. But let's still look. The equations that we're going to generate are exactly the same for the Venturi compared to the orifice. And we're going to see the same thing, that the flow is proportional to the square root of the difference in pressures. Let's look at the rangeability. I touched on it a moment ago. As I said, I'm measuring the pressure right here in this section of pipe. So I know exactly the diameter. I'm measuring the pressure right in this section of pipe called the throat. So I know this diameter precisely. The flow is perpendicular to where I'm measuring the pressure in this venturi. It's called a piezometer. I was the lead engineer for BIF for a number of years in a past life before Siemens, but nonetheless, venturis have a characteristic that there's virtually no wear. Just as an aside, I was doing a presentation in Detroit, and this is back in my BIF days, doing a presentation in Detroit, and one of the fellows, I'm talking about this principle of no wear and how this, and the wear in this throat is the key thing. Once again, the wear on that orifice plate knife edge is what limits it to a certain extent. Just one little aside. This fellow raises his hand and says, hey, I'd like to talk about a venturi we just dug up after 62 years installed. And I'm thinking, oh, geez, here we go. Something's wrong. Something's going to happen. And he said, well, we dug it up, and the certificate we had from, it happened to be a BIF venturi, the certificate we had from BIF that defined the geometry of it, we were within 1,000th of a degree. Excuse me, my cell phone. That's the hotline for application engineering ringing in the background. Somebody will pick it up. Okay, somebody will pick it up. Anyways, the venturi, when we measured it, was in 1,000th of an inch from the metrics that we had from 62 years ago. I bought that guy a drink after that presentation that I was doing. So he made my point. Venturis, basically, if you design them right, don't wear out. It's the key to a venturi design is this transition and the shape of it. How you go from big D to little d. That's the longevity of a venturi. Okay, here's our orifice plate. With the orifice plate, we have certainly the diameter of the pipe is well known. The problem with an orifice plate is, depending upon the flow rate, we don't know exactly the diameter here. Yes, we think of it here as a fixed amount because we designed it and we know how this is going to come out of that orifice hole and then recombine back to the walls of the pipe. I call this, and this is a Lou term, the hydraulic diameter. I like to think of this, as I touched upon earlier, I like to think of this as, remember the garden hose I talked about? When I have a relatively high flow, the plume coming out of here comes out, and with your garden hose, when you open it wide, the plume of water goes out 10 feet. As you close the valve or, change your handle, the squeeze handle, you'll see that it starts to droop. Why? Because the velocity has decreased. It can't project out as far away from you as it did when the valve was open wider and I had a higher flow rate. The same thing happens with an orifice plate. This is fixed. Where I measure the pressure is assumed to be where this diameter is defined. However, if I slow the flow rate down, this whole image backs away toward the orifice plate. Remember the drooping water coming out of the uh, hose in my illustration or my example. This whole thing starts to slide back here, and the diameter is slightly different than I assumed it was. This is also what happens when this knife edge wears. It does not project this quite as dramatically as it does when that knife edge is sharp. And again, I don't know the diameter of the flow stream where I am measuring that flow pressure. And therein lies the issue of repeatability, rangeability. The Venturi, by defining the pipe diameter here and the pipe diameter here, can be a significantly greater change in flow or flow rangeability, however you want to say it, than an orifice plate. And we're going to touch upon that when we look at the differences and the pluses and minuses of these various devices a little bit later in our summary. Okay, that hydraulic diameter is something I hope I've explained properly, that you're understanding it, because it's the key to why an orifice can work 5-to-1, 6-to-1 perhaps, and why Venturis can work 100 or 200-to-1 in terms of flow rangeability. The next thing we want to talk about is a pitot tube. Pitot tube is a little more complex in terms of its derivation of its equations, but it basically is, you see these on the front of airplanes. Next time you're at an airport, look right next to the pilot, his window just below it typically, and right at the nose of the aircraft, you'll see this little L-shaped tube sticking out. Well, that's how he's measuring velocity. And here's how it works. It's literally a pitot tube. We have the Bernoulli equation is what defines how things work in a pitot tube. The Bernoulli equation is a second cousin to the kinetic and potential energy, the energy equation. It looks exactly the same. I have pressure here, P2 or P1, depending upon where you're at. But I have P2 times the velocity here squared. So I have potential plus kinetic. The only thing Bernoulli did was give you a relationship with the height. And I touched upon that at the very beginning when we were talking about the Bernoulli equation. If I change the height of this, then the kinetic or potential energy will change. Okay, but once again, Bernoulli stated that these three elements of his equation were a constant. So if I look at P1 here, I have a velocity V1, and I have, once again, H1 versus H2. The key to the Bernoulli equation relationship to a pitot tube is that these two heights are very much similar. Okay, the pitot tube is they're like a 1/10 of an inch difference in these two heights, and that's a little bit of an assumption we're going to make. So let's see how it works. First off, this is where we're measuring the dP, which is the pressure here at the center, P2, and the pressure around the outside of the tube, which is seeing or sampling the flow at point P1 here, but the pressure P1 versus P2 is the differential we're measuring. Since this is a dead-ended measurement, the velocity at P2 is 0. The density, the gravitational constant, and remember, H2 and H1 are virtually the same, and that's an assumption, but it's the way a pitot tube is designed. So these things cancel out, and then you have left the following, that V1 is equal to a constant. Once again, the difference in pressures, square root thereof. And that's why a pitot tube is a square law device. But the key thing is there's not two velocities involved. There's only one velocity involved, which is right here where it's sampling the velocity in the pipe, and the velocity at P2 is equal to 0. But once again, I have that the area, which I know, times V1 is the flow. So again, flow constant is constant times the square root of the difference in pressures. Let's look at another device called an averaging pitot tube. An averaging pitot tube senses pressures at various points. This, a standard, how I guess Pitot invented his tube, only samples it at a single point. That's what it measures right here, this velocity vector. And I've shown this as a sort of a parabolic shape. That's a fairly low Reynolds number, as it's called. Most of the time in industry, you have almost a square blunt parabola. So sampling the velocity here is pretty indicative of the velocity here. This pitot tube would not work well in this kind of shape. The illustration I was able to get only had this. So here's an averaging pitot tube. It senses pressures across the diameter of the pipe, okay? And that allows it to measure a little more accurately. The cross section of this shape generally is a hole right here in the center. This is a cast plus welded assembly. This shape is unique to different manufacturers, but the principle is exactly the same. The pressure is measured here coming into where the flow comes literally into this port, and because it's dead-ended, the velocity here is 0. The velocity here and here, because I put this bluff body in the center of the pipe, the velocity is measured, averaged here, and then averaged across the entire pipe. But the equations are virtually identical. This just samples the velocities across the pipe a little better than the point measurement of the original Venturi. It was represented a step forward in using a Venturi, a pitot tube to measure the flow. All right. Let's look at some of the advantages and disadvantages of an orifice plate. Let's deal with that. All right, advantage of an orifice plate, simple installation. I stick a couple of flanges in. You buy the flanges with the taps already in them typically, so that you can measure the DP right here across the flange. It has a fairly low cost. It's just a couple of flanges and a plate that you stick in the line, and there it is. It has good repeatability. Provided this edge hasn't worn to where it's a rounded thing, it will repeat, but repeatability is its main forte. As I said earlier, 50 GPM today, it's kind of going to be 50 GPM tomorrow, and I know that gives me good product, so I do that. All right, I have moderate accuracy. It's pretty decent, okay? What are the disadvantages? The disadvantages are typically, I like to think of an orifice plate as a 5-to-1 flow rate. If I'm doing 100 gallons a minute maximum, then 20 gallons a minute is about all I'm going to do in terms of trust it to give me a reasonable measurement, the 5-to-1 flow range ability. It has a relatively high head loss. You see an orifice plate, the next time you install a new shower head, you'll see a little plastic washer they give you with a hole in it. That's a flow restrictor. That is limiting the amount of flow that'll come out of your shower head to conserve water. It does have a relatively high pressure loss. The wear, we talked about that. The beveled edge must be sharp for good accuracy, and that's only because the beveled edge is assumed when we know that 52.4 inches of water equals 100 gallons a minute. But the moment that edge wears, then it ain't 52.4 at 100 gallons a minute, it might be 52. The day after, 6 months later, it might be 51, but you still assume that 52.4 equals 100 gallons a minute. That's the wear on that beveled edge. And it can only work with clean fluids. You get hung up if something comes down the line. This wouldn't work for paper stock, anything with entrained solids. All right, let's look at Venturis. Wide rangeability, typically 100-to-1. As I said, some approach 200-to-1. Very high accuracy because we've defined the diameters and that it's a section of pipe. Low head loss, because we have this section that returns it to the diameter, you don't lose a lot coming through here. There's excellent stability because there's virtually no wear. It can work with dirty fluids because there's nothing to really clog up in here. There's nothing to get hung up. Disadvantage? Yes, it's a higher price. This is a hunk of pipe. This has a fairly long laying length. High installation cost. It's a section of pipe. You've got to put this thing, cut the line, put in a couple of feet, do that. It has a long laying length. They're the disadvantages. Pitot tubes, averaging pitot tube. Simple installation, fairly low cost. It's independent of line size. Yeah, the pitot is a little more expensive, but it can work in rather large, you got a 24-inch pipe. That's a big orifice. That's a big venturi. But in terms of an averaging pitot tube, it's not so bad. Has the lowest head loss of any of the DP measuring devices. I mean, it doesn't restrict the flow whatsoever. Has good repeatability and pretty decent moderate accuracy. Disadvantages, it's probably 5 to 10-to-1 in terms of its flow rangeability. It does generate rather low DPs because you're not restricting the flow in any way, shape, or form. It can only work with clean fluids. You don't want stuff getting hung up and wrapped around this bluff body shape that you put into the line. I hope you understand a little bit better today, right now, how these square roll elements work. The orifice plate, the venturi, common things, flow tubes, flow nozzles, Dahl tube, they all have to do with the shape and the laying length and that sort of stuff. As you get into flow tubes, flow nozzles, Dahl tubes, that 100-to-1 rangeability is going to be sacrificed a little bit, but there's some technical reasons for that. why that happens. Anybody who's interested, just ask, to send a note into the guys at Gilson and guys and ladies at Gilson, and we'll answer that individually. And pitot tubes. You have averaging pitot tubes, a wedge bar, annubar. That's a trademark name. The V-cone is kind of a reverse pitot tube. That I don't see that very often, but it does exist. That pretty much covers square law devices. Now I'd like to devote a little bit of time to remote seals if there are no questions on square law elements. Matt, anything come up?
Not yet. Again,
All right,
everyone,
good.
feel free to throw any questions
Yeah,
in the chat box, and we'll be happy to address them.
okay. Let's look at remote seals. Any of you that heard me talk about transmitters before know how I feel about remote seals. Puh, I hate them. Okay. They are doing two things for you as our customer. Increase the price and decrease the performance. And as I tell my colleagues at Gilson and any of our other representatives, that's not something any customer should thank you for. So they do have their place. They are necessary in some applications, but I always try to avoid using remote seals where possible. And if you learn nothing else from this session, which I hope isn't the case, don't forget, don't just say that's the way we've always done it and continue to use remote seals. After you see what can happen with them and why, what the errors come from, I hope at least you'll appreciate that we try to minimize their use. Why do we need them? Well, some processes will freeze if you have an impulse line that is coming from that process. And take a plastic, take melted Crisco. Fine, you put it in a pipe coming off and put that in your transmitter. By the time it cools to room temperature, Crisco's solid, and that impulse line isn't going to sense pressure anymore. So yeah, you need to have something that's right there at the process so that you're measuring a liquid. Seals can be used to processes up to 660 degrees F. If the process will clog in a small diameter of an impulse line, thing like a plastic, paper stock, those kinds of things will clog and solidify. Sludge at a waste treatment plant, that will clog and solidify in an impulse line. By the way, impulse line is just a half-inch, quarter-inch pipe. I mean, we use the term impulse line for pressure transmitters that way. It's just a pipe.
Blue, one question did come in just asking
Sure.
the upstream and downstream requirements for each of the devices.
Okay. Most of the time we like to say you need about 5 to 6 diameters upstream and maybe three diameters downstream. An orifice probably needs 8 or 10 upstream, and once again, an orifice will be affected by the downstream. So you need like 15 diameters, 10 and 5, maybe 9 and 6 in terms of the amount of upstream versus downstream. A Venturi does a little bit of conditioning of that flow. So the swirls, eddies, that sort of stuff that you do get by coming around an elbow, that shape going from big D to little d, that section of pipe that comes down in that conical shape, does help to condition the flow a little bit and kind of reorganize the flow vectors. The velocity vectors in the flow, I should say. Hope that answers the question.
And anything regarding vertical or horizontal mounting?
No, vertical down you never want to do. Vertical up is okay. uh, for any of these devices. The only thing you have to worry about when you're doing vertical up is the offset you're going to get, because your high and low ports are a physical distance apart. So you guarantee, you know, if they're 2 inches between the taps, you guarantee, and it's water, let's say, you guarantee a 2 inch offset. And that's not a problem. That's just a zero adjustment. But no, never flow down. Always flow up, and horizontal's fine. We tend to assume horizontal for most flows, and that's not always the case. Okay. Um, if the process requires, we talked about why we have remote seals. If the process requires a large surface area to sense the pressure, paper stock, things of that nature. As long as it's a liquid, you will still hydrostatically know the level in that tank because it's a liquid. It's when it solidifies and hardens, or that you don't get the molecule to molecule pressure sensing capability of a liquid. So it's key that way. If you have entrained solids, a flange kind of connection will allow you to use what's known as a flushing ring. Some people call it calibration ring, because you can calibrate a transmitter in situ with it, but I prefer to call it a flushing ring, which is what its main purpose is. And that is to clean this section of sensing diaphragm on that remote seal by squirting, depending upon the process, pumping clean liquid in there. So you scrub that, or air, depends upon the process, what you're going to use, and how you're going to have that flushing ring help you. Whoops, something happened here. Sorry about that, I hit the wrong button. All right, let's look at what is going on. There we go. I don't know how that happened. Let's look at the error sources for a remote seal. There are 3 to 4 primary error sources for any remote seal. First, it's the seal itself. Also, the capillary is a source of error. The attachment to the transmitter is a source of error. And last but not least, the change in height between the transmitter and the seal, this delta height, will also can be a source of error. The major source of error in a diaphragm seal is the compliance of the seal diaphragm. What do I mean by that? Compliance, for you mechanical engineers out there, is the relationship between the diaphragm position and the pressure drop across the diaphragm. What do I mean? Well, what I mean is, as I go and move the diaphragm, here, if you look at this axis, it's cubic inches. Okay, so for a given diaphragm, I know the cubic inch displacement, I know the motion of the diaphragm. This turns out to be thousandths of an inch. I'm not going to go through the math, but here is a diaphragm, and as I move it, the pressure drop across the diaphragm will change. Now, typically, we will operate, or want to operate, down in this region. You never want to get out into this region, which is where things are changing. If you look here, there's a 40-inch change here for a relatively small change in the position. We're always trying to operate down in this region. And how do I continue to operate in that region is key to the performance of the remote seal. The diaphragm diameter, okay, is inversely affecting this compliance term, and the thickness of the diaphragm directly affects this term. The diameter is the third order effect, and the thickness is a fourth order effect. So these are relatively strong effects on this compliance term. Okay, how do we do that? The smaller the diameter of the remote seal, the worse the performance will be. And as I said, that's to the third power. And the thicker the diaphragm is, will also affect this, and that's to the fourth power. So with diaphragm seals, we always say bigger is better. Okay, and that is the main reason. Generally, the thickness of the diaphragm is fairly well defined and held. It's the diameter of that diaphragm seal going from 2 inches to 3 inches usually is what we're doing when we're dealing with flanges. But the difference between that diameter of being around 2.1 inches for a 2-inch flange and 3.5 inches for a 3-inch flange is a dramatic effect on this compliance term. Now, let's see how temperature affects those various error sources we defined before. I had the seal, capillary, transmitter, and head effect. They're all affected by a temperature change because the volume of oil that's necessary to the performance of the remote seal will increase or decrease with temperature. And the volume of oil, the volume of that oil is at least 20 times more than the volume of the stainless steel changes. In other words, the diameter of this capillary, it will get bigger as the temperature gets higher. However, the oil is expanding 20 times more than the hole that it's in. Now that hole's only a few thousandths of an inch in diameter, but nonetheless, it's an effect. So the seal. The seal is mainly affected by the process temperature. That's the effect you're going to see here. Depending upon, say this is 500 degrees, as this oil that's necessarily under that diaphragm expands, I'm moving on that compliance curve that we had shown before. The capillary, the process attachment to the transmitter, and the head effect are all affected by ambient temperature. What do I mean? When I change the temperature of the capillary, and that's largely tied to ambient, that will change the volume of oil once again. And the only place that oil has to go when it expands is moving that diaphragm of the remote seal, because everything else is solid. The fill inside this process attachment, there's a certain amount of stagnant oil there that will cause, once again, this diaphragm to move out here. The change in density because of the change in height will be an offset that changes once again with temperature. If this had no change in height, then the density change would not affect the measurement. I've purposely shown this where the transmitter is mounted below the seal so that I did have a change in height, and therefore the density of this oil changing with ambient temperature will likewise cause an error. Those are the things we calculate when we do performance of a remote seal and transmitter. we use the turn down of the transmitter. In other words, a 100-inch transmitter operating at 50 inches will perform worse than a 100-inch transmitter working at 100 inches. This is why we always say use the right transmitter capsule to minimize this turn down ratio or span ratio. But if you had a 100-inch capsule, you wouldn't want to use that to measure a 2-inch span. That's a turn down of, 50 to 1. Yeah, the transmitter electronics is capable of doing that, but your performance is going to suffer with temperature. Next, the type of seal that you use. What's the diaphragm size? How long is the capillary? What is the process connection? We have to assume a certain ambient temperature change, a certain process temperature change. All of these factors are how we account for the seal system error calculations that we do. They're the main sources and the reason why I hate remote seals. You can't do much of anything about those errors other than accept them and know what they are. And that's what we try to do all the time. Some do's and don'ts. Always use the largest diaphragm possible to get the best compliance. I want to make sure that compliance term is minimized, and that's how I get the best possible performance. Simply use a 3-inch flange if possible. It gives you a nice, big, soft 3.5-inch diameter diaphragm. By the way, going to a 4-inch flange is no advantage. It's still a 3.5-inch diameter diaphragm. All you've done is spent more money on the flange. So 3 inches worth it.
Lou, your audio's cutting
Okay.
out in and out
But
a little bit.
we had a it's cutting in and out.
It sounds a little bit better now. Can you
Are we
talk a little
okay,
bit
Matt?
more? Yep, we're good now.
All right, I'm trying to talk loud. Okay. We want to minimize the length of capillary. Once again, the oil in that capillary system. If you only need, 5 foot of capillary, don't order 15 because it guarantees you're going to have a poorer performance with that 15 foot capillary compared to the 5 foot capillary. And as always, talk to your Gilson sales engineer for help or advice. Gilson's one of the best rep firms we have, truthfully. All of them are got their feet well established on the ground. They do a decent job. Well, I want to thank you for attending this Pressure 102 webinar. I hope it was worth your time. If you have any ideas for any webinars you want, please let your Gilson engineering contact know, and we'll see what we can put together. For individual questions, you can always get the people at Gilson Engineering. Remember, if you want to win a Pressure 103 course, let them know. We can go over things like manifolds, do's and don'ts, remote seal calcs, how they actually look, what some of the errors are for typical situations, and level calculations, how to calculate using a transmitter to measure level in a tank, how you do those calculations. Let's know what you want. And with that, we are finished. I want to thank you for your time. I'd like to thank Gilson for making this possible and spending the time and effort to get you guys here. And I hope it was informative. I tried to keep it simple. I'm a big believer in you never want to make something overly complex. Make it simple to understand, and nobody's worried about the equations and everything else. You don't need to do that. Yeah, some people do, And yeah, we can do that if necessary, but conceptually is what I was after here. So thank you, everybody. Really appreciate your time. We'll go from there.
Just a reminder, everyone, if you do want PDH credit, to send your name, company, and your PE number in the chat. We'll stick on for just a couple more minutes. If anyone does have any questions, feel free to put them in the chat box. And we again appreciate you for your time.